Hi, I'm Kanishka presenting RL-CycleGAN Reinforcement Learning over Simulation to Real. Deep reinforcement learning with robots can do some really cool things. Robots with a camera can see the real world, process it through a deep convolution network, and take actions in the real world. Optimized via reinforcement learning, these robots, through trial and error, can learn to solve real-world tasks. However, such setups can be costly, as large farms of these robots needs to be maintained, and data collection can be a slow process. We can train these robots in simulation, where data generation is much cheaper. However, vision-based robots that see the world through an image or a camera can perform poorly when transferred to the real world, since these simulated images just look very different than the real world. As a specific example of a grasping robot trained on the left side, which is an image from the simulator, performs really poorly when evaluated in the real world, since the image on the right-hand side just looks very different. So it is easy to see why a robot, once transferred to the real world, gets confused and performs poorly. This is the sim to real gap. One idea is to use GANs to close this gap. GANs have been the state of the art for generating really realistic images. So can a GAN adapt the simulated image to look more realistic? This is not a novel idea and has been shown in previous work. And the crux of this problem is this conflict between realism and usefulness. A GAN alone will try to produce the most realistic image. However, if we are to use it for reinforcement learning, it must also be useful. And this usefulness is very task dependent. As a specific example with grasping, the GAN may not move any of the objects or the robot pose, since this would destroy the RL state. In that end, we introduce the RL scene consistency. The idea being the sim to real adaptation is constrained such that an RL agent performs the same outcome in both states. In this way, the adaptation becomes RL or task aware, and we do not explicitly describe what those constraints are. This is naturally handled by the RL agent. We introduce the RL-CycleGAN, which is a CycleGAN that adapts simulation to real and back, jointly trained with RL agents, here shown with Q networks, and the Q networks constrain the GANs to basically have the same output over adapted images using the RL scene consistency. During training, we train the GANs and the Q networks from scratch using data from the simulator and from the real world. And during evaluation, we only use the RL agent trained on real and sim to real images. Here's an example of one robotic setup. On the left-hand side is the images from the simulator, and on the right-hand side are the images from the RL-CycleGAN adaptation. As you can see, the most important aspects for grasping are remained intact. The object locations, the arm, the gripper open close are the same. Other artifacts that are less useful for grasping, like the wires and the background, the GAN has more freedom to adapt as it pleases. We see massive data efficiencies when training with RL-CycleGAN. With just 5,000 episodes, a real robot only performs 15% grasp success. However, if we include images from a simulator and adapt them through this RL-CycleGAN, we see 75% grasp success, a huge improvement in data efficiency. We repeat our experiment for a second robot with a second grasping setup. Again, on the left-hand side is the images from the simulator, and the right-hand side images from the RL-CycleGAN. Again, objects and arm are intact, making it a useful image to learn grasping from. In this setup, we use a baseline where simulated images are mixed in with real images, and you can see at 3,000 episodes, this performs poorly at 13% grasp success. However, if we just adapt those sim images with the RL-CycleGAN, we see a huge boost in performance at 72%. In short, we have presented the RL-CycleGAN that adapts simulated images to be more